Hi guys, I'm not sure where, I'll probably put this in with, along with my tube theory videos, so it'll be like, I think we're on 7 or 8. Anyway, this is going to be on a special circuit on push-pull. It's called screen grid inversion, or phase inversion, for push-pull. The particular one I've got enlarged here and drawn out is off of a Philco 37640 radio. We have, I didn't mark them on here, but these are 6F6s. Both tubes. And we're going to talk a little bit about it, how it works. Now, I just drew basically the circuit of the output here. The signal's being fed from a 6Q7, comes down through a capacitor, then a 70K resistor, and then comes right in to the grid of tube A or tube 1, whichever way you want to call it. And we're going to talk about how we get the push-pull, and a little bit about some of the voltages here and the resistors and stuff. And then we're also going to look at some variations of it that Philco did. This will be primarily, at least in radio, at least back in from the middle late 30s through the early 40s anyway, will be only in Philco radios. They held the patents on this. So how does it work? Well, we have to look at the tube, at a tube, any tube, and look at how the signals reflect each other. When we got a signal on the grid, excuse me, we need to look at how that is, it is to the screen grid, the plate, and the cathode. So, as far as phase goes, when you got a signal on the grid, it's in phase with the cathode right off the bat. So, if this was going positive, now the cathodes are tied to ground, so you're not going to really see much there, but the two are actually, they'll be in phase with each other, which means also the suppressor grid on the pentode, since it's tied to the cathode on a 6F6. As far as the grid to the plate, they're out of phase, 180 degrees, and we'll get to why that is here in a minute. But what about to the screen grid? Well, they're out of phase also, 180 degrees. So right off the bat, I've got something here that's 180 degrees out of phase that I can make use of. So if I've got a signal like this, can't draw a line through it, my drawing's not the best, then on both the plate, which will be greatly enhanced and much stronger, which I won't be able to draw in here, there, but also on here on the screen, which won't be as much amplified. So when this goes negative, the signal's going negative, both these go positive. Now why is that? Basically, when if the signal's going negative, that means the grid's getting more negative. And the grid gets more negative, less current flows through here. Less current flows through here means when I look at the plate, I've got a load over here. Okay? There's an impedance load here. When there's less current going through, there's less voltage drop, because B plus is hooked right here. So this thing drops less voltage. When it drops less voltage, more voltage is available at the plate. So the plate goes positive. On this screen grid, same thing's going to happen because I've got a load resistor. 3.5K, 35 ohm load resistor here. So when there's less current going through here, then there's less voltage drop here. Less voltage drop means more of the B plus gets back to the screen. It goes positive. Increasingly more positive as this increasingly goes more negative. When it starts going positive though, then that means the grid is becoming less negative, so it's not opposing the current, the electrons coming from the cathode. So more current flows through the tube. When more current flows through the tube, we have a greater voltage drop on this load. We have a greater voltage drop on this load. So that means less voltage to the plate, less voltage to the screen, so then they drop. They go negative. Now that's with respect to the signal only. This line would be basically the baseline voltage that they're on with no signal. I can make use of this because this is out of phase with this, so which means it's in phase with this. But if I feed that down, run it through a coupling cap, and feed it to here, it's the same phase as that. So now this grid is doing the same thing. It's going like that, which means here, which you're not going to see, I'll go up here, which means on the plate of this other tube, tube B or number 2, then it's going to be going the opposite direction. Now, it's going to be a bigger signal just like that one is. I just didn't have room on here to draw them in because it's amplified. So, consequently, I've got my out of phase situation here that's needed by the transformer to operate in push-pull. So, and it truly is true push-pull in the fact that when this tube is pushing, in other words going positive, this one's pulling, going the opposite direction, negative. Now, in a nutshell, that's how it works. There are a few things that we have to look at, though, and that will vary with the tubes that's used. There's various different tubes that can be used in this circuit, and so we have to look at those. Now, first of all, this is Class A, although I will show one where it is Class AB1 that is using the screen grid inversion. So screen grid inversion will work with either Class A or Class AB1, even Class AB2. Not real good at Class B, but it will work. But this particular one is Class A, which about 60% of all push-pull audio amplifiers and radios were Class A. Class A gives you the greatest fidelity, so that's why they used it. Now, your signal path, the signal's coming in here and going this way. Well, we have a resistor here, we have a resistor here coming down to this grid. Why don't it go this way? Well, the reason why it don't is this is a load resistor for that grid. That's what it's acting as. It comes down through here. As far as the signal is concerned, not DC, signal. So this is AC. As far as it's concerned, it goes to ground here. Return path. Same thing here. Why don't this interfere back up this way? Well, because this is going to be going over this load resistor here and back to ground. Return path. Now, there's a 490K resistor here that is connected to a voltage source. That voltage source is a couple resistors that's in the center tap of the high voltage secondary on the power transformer, and they're there before the secondary. They're between the secondary and ground. They're there for the purpose of creating negative bias voltages. This pulls off one of those taps, gives us minus 16 volts. Minus 16 is perfect for class A for 6F6. And we got just a standard pull down resistor here of 490K to keep both these grids at that minus 16. That's with no signal. That is your operating point for biasing. Now you notice that there's two different size resistors here, and that's because the fact that they're using a 6F6 tubes. The 6F6 has quite a bit of actual current on the screen grids. In fact, it runs zero signal, the zero signal current at these voltages the plates and the screens are running at is around 6.5 milliamps, and at full maximum signal is about 10.5 milliamps. It's a pretty sizable current. These are different sizes. Now realize, under normal circumstances, practical circumstances with no signal and nothing coming through, all we have is just our DC voltages on the tube, then there is no grid current. But when you have a signal, that signal is making a pathway back to ground. Okay, there's a completed circuit. There is a current flow. So there is some voltage drops here. These are set up the way they are these are the loads. This is what develops how large this signal is going to be here and here, because of the size of these. Being the current is high enough here, it's working out to be about a 1 to 2 ratio. This is about twice the size of this resistor. Then being that's why they put the sizes they put in here and designed them to reduce the size of this signal, because this one is going to be slightly amplified on a 6F6. So this is going to be a little bit bigger than this, and I can't have it. I need them balanced. So what this is actually doing is the balancing. It's balancing the circuit out. With the 6F6s, it runs about somewhere in the ballpark around 2 to 1, 1.5 to 1, somewhere in there. And there's no actual real math for this because there are no characteristics for the screen grid. Tube manufacturers never actually created any characteristics. The only thing you've got is plate characteristics. You don't have and grid characteristics, but you don't have any screen grid characteristics. So experience and stuff like that kind of gets the engineer in the ballpark. The rest of it is experimentation. And what they'll do is they'll actually play with these values to look for a range of values that can be in here, and they'll pick the middle of that range or as close as possible. These are not critical, dead critical. They don't have to be like 1% resistors or even 5% resistors. In fact, it surprised me if they're even 10%. Generally they can be 20%. The tubes are forgiving. The currents in here fluctuate a little bit, not always exactly what is marked in the manuals. So these can be played with. Plus the values that are here is actually the mid-range. So there were some values quite a bit lower than this in this one, and some values quite a bit higher in this. There was, a little bit of fluctuation that they could do. And they picked the mid-range so that both the resistors could drift a little bit, be off a little bit. Knowing in manufacturing you're not going to pick 20 resistors all the same exactly. So no two's going to be that close. So there's some definite wiggle room here. But they are different sizes because of the fact there's more current on with a 6F6. Now I'm going to show another schematic where they're using 41 tubes, which have a lot less screen grid current, and they're actually balanced. The resistors are the same size. But that's what the resistors are there. They're actually the load that develops, allows the signal to be developed. The voltage here is actually being developed across here. So that's what you're seeing at here and here. And that's why these values are different, because of the fact that it's 6F6 and this signal's roughly about 2 times larger than the grid that's going in there, roughly. You know, it varies a little bit. Now, I want to talk about some things. I was going to make this video a lot sooner, like a couple days ago, but I read some stuff that kind of bothered me, and I needed to do some research on it. There's been some talk going around that this screen grid inversion circuit could be harmful to an audio transformer. That's really a correlation thing. In other words, evidently a few people's gotten, you know, there are several models made that use this with various different tubes. But in any case, there's evidently a few people's gotten some radios. They had a bad audio output transformer, open primary on it, and someone started trying to make some association and started blaming the circuit. That is not the case. There are 2 primary reasons for an audio output transformer to be bad in these old radios. First of all, this is roughly a 1936-37 radio. This thing is well over 70 years old. Okay. In fact, a lot of these radios, you know, they're 70 plus years old. Actually, more than that. Getting close to 80. And a lot can happen in 80 years to these transformer windings. So that's number one. They're old, okay? But the 2 main culprits that takes out an audio output transformer, there is a problem with this circuit. And a lot of radio, not just Philco, every brand out there used this and did this. They also did it another way, which I'll show here in a little bit and explain why it's better. You see these caps coming off the plates? It comes off this plate, goes to ground. This one goes off the plate and goes to ground. You can't really see that one, sorry. Well, here. This one down here goes to ground. There's 2 of them. These are tone correction caps. They're there for both tone correction coming through the audio amp and the audio amp itself, as well as some stuff on the audio output transformer. The only problem with them is where they're connected. These are paper caps. They're connected right to ground. What's on the other side of them? B+. There are 250 volts of B+ here. About nearly 100 milliamps, almost, on this particular radio. So, most of you know, and the ones who don't know, I'm going to tell you right now, these caps get very leaky. Paper caps leak. Okay? With age, they dry out. The wax starts breaking down and drying out, which is what kind of keeps them from moisture getting in there. The moisture gets in there, it starts deteriorating the paper, and then the darn things start leaking through, arcing through. They just get leaky, and they can get really leaky. They can even short. I've had caps that, paper caps like this, where just my digital ohm meter, digital DVM, put it on continuity test, it'd buzz it. So, dead short. If this thing is either extremely leaky or dead shorted, it's going to take this winding out. This is very fine wire that's in here, and I guarantee you it'll go out before this cap does. So that's the number one culprit right there, is those caps. And the bad thing is, when you get the radio, you have no idea what has been done to it, what has happened to it. 5 years ago, someone could have plugged it in, that cap shorted, one of them or both of them was shorted by that point, or extremely leaky. Anyway, it took the audio transformer out. You get the radio off of eBay at some auction, or off Craigslist, or wherever you get the radio from, you know, and then you go start testing and find that the audio transformer's out of it. The other problem with transformers, and not just audio transformers, but a lot of different power transformers as well, is the fact of their age, and the fact that the environments they may have been stored in. Unfortunately, not all radios are stored in the same room that they were brought home to and put in when they were first bought, or at least in the same house, where at least there were some controlled conditions. So humidity goes up, corrosion might start, these things get, you know, inside that transformer, between each layer of windings is paper, and it can draw moisture. And if you get real high humidity, you can get some decent moisture getting drawn in there. At each one of the connection points, the enamel's off the wire to solder on the connecting wires that comes out to the rest of the radio. So those points can corrode because of moisture. You know, these radios can be stored in, they can be found in a lot of different places. Old barns, attics, wet, damp basements, garages, unheated, and all this stuff. Any number of places. And after many, many years of this, can take a toll on that transformer. What can you do about it? If the transformer tests good still, the one thing you can do is, if it's got shells on it, get the shells off. Clam shells. Those are the little metal covers that covers over the transformers. A lot of these newer audio transformers, what I mean newer, in the later 30s and on, generally didn't have clam shells, which is perfectly fine in one regard. In any case, let them at least acclimate. In other words, get used to the dry environment and dry out in your house. If you got only air conditioning in certain rooms, like window air conditioners, that's one place I would put the darn thing. But for a while, at least, a few months, anything, so that they can dry out. If you're in a big hurry, you can actually disconnect the thing, take it out of the radio, and put it in the oven at real low temperature, the lowest setting you can get, and leave it in there for about an hour or so. It'll help dry them out. If they get dried out, then they're not as likely to cause any problems. Always be wary, though, there can be some corrosion. If you see signs of corrosion, it'll generally be where the wires connect on to the windings. You know, try to treat that corrosion, try to get rid of it, and try to get something on there to protect it so it doesn't continue to corrode. But those are the two main culprits. It has nothing to do with the circuitry. It has nothing to do with what type of push-pull is being used. It has nothing to do with whether it's Class A, Class AB1, Class AB2, Class B. It makes no difference on what type of operation is going on here as far as the longevity of that transformer. The transformer is not underrated. I read that somewhere, that they thought Philco was trying to save money and underrating their transformers. No, they're not. Because that was the case, they'd had a lot of warranty repairs. They wouldn't have done that. No. It's the caps, or just pure age and bad places of storage. is what generally takes these out. Of course, there's one last little one that can be very much so. A lot of these might have been underneath the chassis, and I had a couple like that rodents got to. Some mice got in there, made nests, and lived in there. And the thing about rodents is they got to chew on stuff. Their teeth continually grow, so they're always looking for something to chew on to grind them down. Well, these transformers and the wiring in there and everything is a perfect candidate, and they will chew up a transformer in a real big hurry. Generally, the primary may be alright. It's the secondary that usually gets damaged on that in that case. Now, so why even do this? Use something like this. Well, for one thing, you reduce by one tube. You don't have to have a phase inverter tube, but there's other circuits that you can use, other ways of doing this that you don't have to have a phase inverter tube either. There is a slight increase. These actually do have a slight increase in power output. They also, only because they're reducing third harmonic distortion by a slight little bit. They reduce it because there's a certain innate feedback right here, negative feedback actually going on in this circuit, because of the screen grid feeding back to this one here. It actually reduces odd harmonics, mainly the third harmonic. Even harmonics you don't have to worry about because they're taken care of by the transformer. It's push-pull. Even harmonics will be removed real quickly. They cancel each other out. So there is advantage there. And that gives them a slight little step up on some power output. The other thing too is well, they do really work really nice with Class A and Class AB1. Their Class A is used quite a bit because of fidelity. It gives the best fidelity. It's not the most efficient amp. It's the least efficient, but it is the best on fidelity. And these do sound really good. They got excellent fidelity. The other thing is you do reduce a little bit of component count. The circuit's more simple. Something that's more simple has less things to go wrong with it. It's also more forgiving if something does get a little bit out of whack. So that helps a little bit. I think the primary reason was it was something that Philco, through Hazeltine, which basically was their development team outfit, but anyway, could develop and patent and hold that patent and not let anybody else, fight anybody else getting with it. I think it was a marketing thing more than anything else. There are a few little advantages to it that can be marketed, and of course let marketing have it and they'll make it even better or sound better. But I think that's really one of the primary reasons. It wasn't to cheapen the radios, because I'm going to show you where they actually, a lot of these same radios during the time they would sometimes they would go ahead and use a tube in there and use a tube phase inverter with the same, on these radios. They just take out this resistor here and take out this capacitor here, and then we just put a phase inverter in to operate. The big thing about less tubes really is not that big of a deal, as far as it actually can hurt your cells, because during this era tube count was a big selling point, and that will stay that way. You will see that all the way through the 40s, the 50s, into the 60s. You'll also see it fall over into transistors and transistor radios. That's why you'll see a lot of transistor radios that they make a big ploy out telling you how many transistors is in that radio. And it's a selling point. People got in their head, and to a certain extent they had reason to, but they got in their head that the more tubes, the better the radio was. And to a certain extent it is. But this is also why some radio manufacturers actually went as far as put, instead of having a full wave rectifier tube, and they took 2 half wave rectifier tubes and put in. Gave them another tube. I tubes, they were in there. The reason why they were there was because it's another tube. So a lot of manufacturers started pulling little tricks like that. Philco was not any different. They had, sometimes they would use 2 tubes in place of 1. That was not unusual. So what is the disadvantage of the circuit? It does not work with beam powered tubes. Beam powered tubes are tetrodes that are specially designed, and they have beam forming elements built into them, as well as the fact that the grids are perfectly in line on the same plane. And they're a lot like this. If this is this control grid, your screen grid will be in perfect alignment. This way the electrons flow right straight through, almost like they're beaming through. That's why they call them beam powered tubes. Problem is, you get a lot less current, almost zilch current on the screen grid. Without that current, this circuit doesn't work. No current, no voltage drop on the load resistor, no voltage drop in the load resistor, I can't develop a signal. There were some companies that tried using beam powered tubes. They ended up with really basically with a single ended amplifier with an extra tube just going for the ride. On your regular Pinto tubes, they're out of line. This is your grid, control grid, this is your screen grid. So you get a lot of the electrons will embark and can hit the grid by just simple impact of the screen grid. So let's see here. Alright, I'm gonna kind of adjust you here a little bit, so bear with me so I can show you some other stuff. Gonna bring us down, and we'll try there first. Here's another. Sorry that the schematic's kind of small. I'll try to zoom in on the main portion of it. This is just another form of the same circuit. Instead of 6F6s, it's using 42s. Here's those 2 resistors, except they're larger valued here. We got, I think it's a 330 and a 490 Ks, but that's the 2 balancing resistors and stuff, but it's the same basic circuit. A 42 is basically the same thing, well, it is the same thing as a 6F6, identical. And so the signal comes in. In this case, we're running on the other radio. Was running the first audio pretty hot at 175 volts on its plate. This one, same tube, we're running 100 volts. So we don't really need an inline resistor to kind of reduce that signal, so we don't overdrive. Instead, they just got a standard plate resistor here. Signal comes in, feeds through, comes through, and back out through here, drop across, feeds down to this grid, then we have the 2 going out. Again, same design, got the 2 caps here, which are bad. But like I said, they're not the only ones that did this. Now, I'm going to show you a couple other radios. We got to kind of do a little adjustment here. Let's see if I can get lined up on it. And kind of get ourselves settled down here a little bit. So bear with me. I'll back out just a little bit and then I'll zoom in. I want to back out and just show the power supply a little bit here. I'll move down here a little bit and see if I can kind of zoom in just a little bit. Alright. This one here, and I'll zoom in on the tubes, but this one here is using 41 output tubes. These are the same thing as 6K6. They run at a little bit, or they can run a little bit lower voltage. They have less screen current on them. So in the case like that, it actually has two 1 megs. The two balancing resistor, load resistors for the grids are exactly the same size. Those grids, along with several other negative voltages, are developed right here. The grids for the output tubes is developed right here. The current flows through here, through all three resistors. This is the most negative portion. I believe it's about minus 14 volts for these tubes. Then the other two feed up for different tubes. We've got this tube here. The first audio is getting its fixed bias right here, coming around here, which is about -1 volt is what's being dropped across here. This radio is also kind of something that they did just to add tubes. Basically they're running split ABC. This tube and this tube both are producing an ABC signal. We have the two diodes here, and it's rectifying, it's pulling some signal back from here and rectifying it and running the ABC signal down to the very first tube, which is the mixer or first detector, and then off the second detector, just a regular detector tube, we have the other branch which feeds over here to the first IF. Kind of just a little different design. It was just a way to add in some tubes. The other thing too, I wanted to show you, that last schematic before this one with the 42s, that one's actually an AB2 amp. It is running a little, it's running about -22 volts to the grids, so it has shifted the point or operating point, so it's out, it's not class A anymore, it's class AB1. Now the other thing I want to show on here, but I'll zoom in so you can see the circuit a little closer. One thing I want you to pay attention to is FGH. It's the FGHJ, these letters here, and also these over here, but primarily these, because we're going to show something on the next page. But let me zoom in here so you can kind of get a little better view, and we'll kind of again walk through this circuit just like we did the other one. These are not complex circuits. Basically we're just making use of the fact that when it comes to the grid, the screen grid, as far as the control grid, the screen grid and the plate are out of phase. That's really the important factor here. So basically it feeds the signal in, coming in, feed in here. Of course that gets amplified and goes on out, but also some of it picks up off of here. Again, on the 41 tube, which is 6K6, there's less current on here, so the balancing resistors can be the same size. This feeds down, has a voltage drop across this resistor here, which is what's going to be showing up on this grid here. These two signals, this signal here and the signal that's being developed here, will be virtually the same size. Since this is quite a bit lower current, these run about between 2 and 3 milliamps on the screens. So they're a lot more in tune with the 766 First Audio. So this will be out of phase with this grid. So this grid and this grid now are out of phase, which means these two plates will be out of phase with each other. Otherwise, the circuit's the same and operates the same. Now we're going to show you something else. Let's see. Now the biggest thing I want you to notice on here is I'm going to show you two circuits, and I'll get this darn thing kind of situated. Alright, this first circuit we're going to look at is what you may be more used to seeing. Phase inverter, number 37 tube. Same 241 outputs, same 1 meg resistors here. Oh yeah, and the other thing too, this is the same here. This cap goes across from plate to plate, nothing going to ground. This is by far safer for the audio output transformer than the other design where we're dropping one cap off the ground and the other one off the ground. This one goes from plate to plate, so if this thing shorts out, it'll just open. In fact, when it just gets really bad and leaky, it will just overheat and open up and pop an end off. It will not damage, or less likely to damage, the winding. But anyway, the big difference between this and the other circuit is the fact that here the screens are just connected together and feed to B+. But notice, and I don't know if you can see it, nope. We have the same letters here. This is just a circuit alternative. There's like 4 different models that they've got on these 2 pages. But the voltages to here are identical. It's the same power supply. It's just that they actually took the circuit and tied the screens together, got rid of the resistor and cap, and then added in the phase inverter. Now, one other thing about the phase inverter is, here's another example of what goes on about inside a tube. You know, in here we talked about the control grid being 180 degrees out of phase with the screen and 180 degrees out of phase with the plate, but I said it was in phase with the cathode. Which is the case here. This is how this phase inverter works. We feed the signal in the grid, but we have one signal normally coming out, just your normal route coming out of the plate, over to this grid. But this grid is fed by what's coming off the cathode. Because what's on the cathode is in phase with the grid, what's on the plate is out of phase. So now these two are out of phase. And we just add in some resistors and stuff to balance it out and everything so that the two signals are the same strength going in. But right next to it is yet another circuit. Now if I can get the thing to move, there we go. Here, back to the old circuit. But this one's a little different than the one above because it's just got one tube acting as detector, AVC, and First Audio. Where the other one on the page before this had 2 tubes here, this has just one. But we're back to the screen grid inversion here. So, they had about 4 different models here, a couple, 3 different ways of doing things, depending on how many tube count they wanted for a particular radio, and depending on what other markets that they were dealing with and what they wanted to market to. So I hope that explains how this circuit works. It's not real complicated, and it's just based off the simple fact that when you're comparing to the grid, to the plate and to the screen grid, they're out of phase. And since they're out of phase, all you got to do is take and pull some of that signal off, feed it through a load. You have to have a load because this is just current. Current comes out of a tube, but the grid needs to see voltage. So you have to feed it through a load to get that voltage. Anyway, that gets impressed on the grid of the other tube, giving us our out of phase of the two grids. If the two grids are out of phase, two plates are out of phase, then they can feed the audio output tube, or output transformer. But some of the things, these work just as good as the other, if not a little better. They don't have any real serious disadvantage other than the fact that they cannot be used with beam power tubes, and because of the reasons I explained, and that's their only real disadvantage. They do not harm. This is the same darn transformer, everything's the same. They will not harm the audio output transformer. They won't do anything. They didn't do this to cheapen anything or anything else. So they're good. It's a good operating system. I've got 2 radios, I believe, that has it, and they sound just as good as any other radio that has a regular push-pull, because they are nothing but a regular push-pull circuit. So I hope I was able to explain it. If you do have any questions or anything, I can go over it again and stuff, and try to hopefully do a better job explaining it. So I want to thank you all for watching, and thanks for your comments. I've got a few new subscribers. Thank you to my new subscribers. If you like this video, give it a thumbs up. And if you're new to my channel, I do stuff for theory. I also restore vintage tube equipment, TVs, radios and stuff, and I do videos on that. And so if you kind of like that kind of stuff and you're new here, just go ahead and click subscribe, and then you'll be posted knowing when my new videos are coming out. So until then, guys, thanks for watching and have a good week, and I'll see you on the next video.